Welcome to my channel. Today, in this session, let us discuss about the asynchronous ticket counter. Already we have discussed about the asynchronous 2-bit counter and also we have explained about the 3-bit counter. Today, in this session, we are going to discuss about the asynchronous ticket counter. As name itself, it is given that the counter which counts the decade states, that means the 10 states from 0 to 9, right? So the counter which counts the 10 states is named as the decade counter. This is given here. A decade counter with a count sequence of 10 states are called decade counter. Okay, and the states are nothing but it starts from 0 and ends at 9, that means 0000 through 1001. This counter, since it counts from 0 to 9, it is said to be as the BCD counter because its 10 state sequence is the BCD code. Okay, so and with this, let us discuss into the logic diagram and the timing diagram. This counter, since it counts from 0 to 9, it consists of 4 flip-flops, right? And it this is also one of the method of achieving recycling after the count of 9 to decode the count 10 with the NAND gate and connect the output of the NAND gate to the player. So here also similar to that of the 2-bit counter, there will be a recycling, right? So the recycling process happens by the means of the NAND gate, right? The recycling is nothing but the counter here counts from 0 to 9 states and the next state is recycled as 10 as 1010 with the help of the NAND gate. The gate is connected to the clear bar. The clear instruction is the low instruction, right? So, this is well explained in the logic diagram. This is the logic diagram. As said earlier, the counter which counts from the states 0 to 9 and the flip, it consists of 4 flip-flops. The flip-flops are named as flip-flop A, B, C and D. Okay, and J and K are connected to the high. That high, it seems to J is equal to 1, K is equal to 1. If these two are 1, as said earlier, the flip-flop, the logic JK flip-flop logic is nothing but when both inputs are high, it seems to be toggle, right? Similarly, in all the 4 flip-flops, J and K input are high, it toggles. And it is provided with the clock input. The output of QA is provided as the clock of the next section. And it counts from the states 0 to 9 and for the next recycling the output is connected towards the NAND gate and the NAND gate output is nothing but low output, right? And it is made to reset by this manner. Okay, so it since it counts from the 0 to 9 states, we are providing the pulses and at the positive pulse next clock pulse is triggered and similarly for the QA positive edge QB is triggered and for the QB positive edge QC is triggered and for the QD. Finally, it is made to reset. So I repeat it once again. For the decade counter, it counts the 10 states, that is from 0 to 9. Since it counts the 10 state, it is constructed by the means of 4 flip-flops and as in the earlier cases, the J here also the JK flip-flop is used. J and K is made to high and once it is made to high, automatically it we know the condition that when J input and K inputs are high, it is made to toggle and in for a single flip-flop, the clock input is provided and the output of the first flip-flop is taken as the clock pulse for the second flip-flop. So due to this, when there will be a propagation delay and the propagation delay is mentioned in the timeline diagram, right? And for recycling is the main happening in the case of asynchronous counter. It is nothing but the delay. And for recycling, then we are providing an NAND gate, and this NAND gate is connected towards the output of QB and QD. The output will here will be a low output, and it is made to provided to all the inputs, all the flip flops, and finally after the 0 to 9 it is made to reset, right? And this is explained in the next cases. That means in the logic diagram only QP and QD are connected to the NAND gate, right? And this is the example for practical decoding also. So the decade counter, synchronous counter, which we have explained, is an example for the partial decoding, and which have two unique ports. Since it is said to be as the partial decoder, as since it has the two unique states in the sense it has the same states. For QB is equal to high and QD is equal to say. So if this is the condition, it decodes the state 10. 10. The base 10 denotes that it is nothing but the decimal equivalent value, right? When the counter goes into the count of 10, the decoding gate output goes to low, right? And it resets the all the flip flops in the counter cases. Okay, so asynchronous counter is similar to that of an BCD counter. It consists of four flip flops, and in the four flip flops, the input is provided to the one clock pulse. Sorry, the one flip flop. Clock pulse is provided to the one flip flop, and the output of the first flip flop is given as the clock input of the next flip flop, and the flip flops inputs J and K are tied to the high, and if both inputs are high, if both inputs are high, automatically we know in the JK flip flop, if both inputs are high, it makes to toggle. Toggle in the sense it's makes to transit. That means it makes to change of state, right? So the output of QA is for the clock of the next session, and due to this, there will be in case of propagation delay, and the timing diagram is given for the counting of 10 state. The positive edge of the first clock pulse is provided as the triggers the first flip flop, and the positive edge of the next triggers the next flip flop. So, and finally to reset, the QB and QD input are connected to the NAND gates, and the NAND gates are the output is clear bar. Clear bar is low, and it resets the four flip flops. That means it counts the output, decayed output of 10, right? So with this, we have discussed other than the asynchronous counter, 2-bit counter, and 3-bit counter, similarly and decade counter. So viewers, be thorough with these counters. It seems to help in your objective session, right? If you like this video, like, share, and subscribe. Thank you.